So section 2.3, a section that I think you're going to really like. I got all sorts of good news for you in this section. In the last section, we learned how to calculate derivatives, a hugely important task that was really challenging algebraically. We used the difference quotient to come up with a few different results that I copied over here. At one point, I gave you the function x squared minus 4x plus 1 and asked you to figure out the derivative. And after, I don't know, damn near a whole page worth of algebra, we came up with f prime of x being equal to 2x minus 4. And no matter how many times I tell you this is super important and it's really interesting, you're probably like, yeah, I don't know if it's really that interesting, or at least not all the work that I had to do to calculate this derivative. And this one wasn't even that bad relative to some of the others we did. We also figured out that the derivative of 1/4 x cubed minus x plus 1 was 3/4 x squared minus 1, and then looked at some rational functions and some radical functions. It was super hard. In this section, I want to reproduce those results, but take a completely different approach. Rather than do super complicated algebra, I want to just kind of look for some patterns. Like, if you compare this function and its derivative, you might notice that we had a negative 4x term right here, and we also had a negative 4 right here. Maybe that's just a wild coincidence, or maybe there's something going on here in this function that would allow us to predict that there'll be a negative 4 here anytime we see a negative 4x here. You're probably pretty skeptical, but I might add that we had a negative 1x right here, and then we had a negative 1 over here. Maybe that's more than just a coincidence. Maybe there's something about this x squared right here that produces this 2x right here. I mean, we got a 2 up in the exponent here, and then we have a 2 as the coefficient right here. Maybe that's more than just a coincidence. If that was more than just a coincidence, you might expect the 3 that's up in the exponent right here to kind of appear over here in the derivative. Maybe that's this 3 right here. Maybe if we view 3/4 as 3 times the 1/4 that's hanging out right here, we can kind of see where some of the parts of the derivative are coming from just by looking at the function. And you might be like, yeah, but what about this plus 1 right here? Where does that show up in the derivative? Maybe I just draw an arrow way up here to sort of indicate that it disappears for some reason that we'll understand by the end of this section. Similarly, this plus 1 right here has nothing to do with this minus 1. This plus 1 just kind of goes away as well. But I'm getting way ahead of myself. Let me take this one step at a time. What if I told you that the derivative of this function, x to the 5th power, was 5x to the 4th power? And I didn't draw any arrows or anything like that. I just said this is true. If you use the difference quotient and put x to the 5th in and did a ton of algebra, trust me, I'm your teacher, 5x to the 4th would come out. If I told you that was true, and then I asked you what the derivative of x to the 6th power might be, and you're like, oh, really? You want me to set up a difference quotient? I was like, no. I don't want you to calculate this. I want you to guess at what you think the derivative of x to the 6th power might be, based on some results that we've come up with already, and this thing that I'm telling you to kind of trust me about, that the derivative of x to the 5th is 5x to the 4th. While you're thinking about that, maybe coming up with a guess for what you think the derivative of x to the 6th power should be, I want to teach you some calculus notation, because it'll end up being super useful. It's kind of annoying to have to say, what is the derivative of x to the 6th power? And you're like, you don't have to say that. You could say, I don't know, f of x equals x to the 6th, calculate h prime of x. I'm like, yeah, you could do that too, but that's a lot of writing. It would be nice if there was some, like, I don't know, symbol that meant take the derivative of. And it turns out there is. The symbol that we'll use in our class, there's a few different ones, is d divided by dx. And usually these aren't written as the letter D, it's a del, a kind of made up math symbol that's like a D but it doesn't have a little tail on it, but it doesn't really matter. D divided by dx kind of looks like a fraction. You're wondering about the variables and what's going on. Don't think about any of that stuff. This is all just one symbol and it means take the derivative of. So how would I use such a symbol? Well, up here, this sentence that I wrote out in English, that when h of x equals x to the 5th, h prime of x, the derivative of h of x, equals 5x to the 4th. I could capture all of that information by writing the derivative of x to the 5th power equals 5x to the 4th power. This notation will not only be kind of shorthand for now and save us some time, but it'll be especially useful when we learn how to take derivatives that are multiple steps. And I know you don't really know what I'm talking about right now, but trust me, you're going to really like this notation. Make sure that you can read this. The derivative of x to the 5th power equals 5x to the 4th. And if you can read that, then instead of saying any guesses for the derivative of x to the 6th, I could say something like evaluate the derivative of x to the 6th power. And maybe now, without further ado, I can just tell you what the answer is. It turns out the derivative of x to the 6th power is 6x to the 5th power. Normally in a calculus class, I would prove this for you. I would show how you can come up with this general result, and most of the students, if I'm being perfectly honest, probably wouldn't follow the proof, but whatever, I feel like I did my part and I've proven it for you. The nice thing about a business calculus class is I'm not asked to prove results for you. We focus less on why things are true and more on the key results that we need to apply in a business setting. So while I still feel a little bit uncomfortable doing so, I'm going to tell you to just trust me that this right here, which is called the power rule, allows you to take the derivative of your variable raised up to any number that you want. So think about this as kind of a formula where n can be any number that you want. If I ask you to, evaluate the derivative of x to the 20th power, it'd be nice if you could look at this and immediately know that the answer is just 20 times x to the 19th power. This rule is super useful in evaluating derivatives, and we can kind of see it in part of the results that we figured out in the previous section. This x squared changing into this 2x is really just an application of the power rule. Because think about it, the derivative of x squared. What do? I take the exponent, the n, which is a 2 in this case, and that becomes my new coefficient. The exponent comes down in front if you want. So this 2 comes down in front, and then I still have the letter x, but it's no longer raised up to the second power. It's no longer raised up to the n power. It's raised up to the n minus 1 power. You subtract 1 from the exponent if you want to say it that way. So it's 2x to the first power. But when x is raised up to the first power, you don't even have to write that exponent. It's just 2x. This x squared turned into this 2x. We don't have enough rules to get this complete derivative of this function, but we can at least pick on one little part of it and kind of see where it came from now. That's what's called the power rule. The second rule I want to show you deals with coefficients, and it works really nice in conjunction with the power rule. What if I asked you to figure out the derivative of 4x to the 5th power? You're like, well, I know the derivative of x to the 5th power, right? I can use the power rule. But what about the 4? What do coefficients do in terms of the derivative? Well, let's see if we can figure it out just based on an example that I'm telling you. If you put 4x to the 5th into the difference quotient, 30 minutes later after a ton of algebra and you being kind of upset with me, you would come up with 20x to the 4th as the derivative of this function. Can you see all the different pieces? We know that x to the 5th is going to turn into 5x to the 4th. So does it make sense that 4x to the 5th turns into 20x to the 4th? Well, yeah, because 20 is just 4 times 5. It kind of looks like this coefficient just ends up being a multiple in the derivative. So if you had to take a guess for the derivative of 10x to the 20th, you might think, well, just take the derivative of x to the 20th, which is what, 20x to the 19th, using the power rule? And then take the 20 times the 10 to get 200. You might think that the derivative of 10x to the 20th power is equal to 20x to the 19th power. And in fact, it is. When you have coefficients and you're taking derivatives, the coefficients don't come into play. What do I mean by that? Maybe it'll help if I write this up in 2 steps using our new derivative notation. The derivative of 10x to the 20th power is just 10 times the derivative of x to the 20th power. When you have coefficients, you can bring them out in front of the derivatives. This 10 doesn't interact with the derivative at all. The derivative of 10x to the 20th is just 10 times the derivative of x to the 20th. And the good thing about the derivative of x to the 20th is we know what it's equal to. It's equal to 20 times x to the 19th power. So rather than jumping straight from here to here, if we read it up in a few steps, we can really understand the process, and understanding the process will allow us to apply it more generally. If you're the type that likes formulas, I can give you this. When a is a constant, the derivative of a times any function is just equal to a times the derivative of that function. And that might help you, or that might just confuse the matter. It might be easier to just remember an example like this. And we've actually seen this already. Remember this 1/4 x to the 3rd power part of this polynomial? Now that you know the power rule and this coefficient rule, we can evaluate the derivative of 1/4 x to the 3rd. We take the 1/4 out in front, and then we'd multiply that by the derivative of x to the 3rd power. You know the derivative of x to the 3rd power because you know the power rule. It's 3x squared. So the derivative of 1/4 x cubed is 1/4 times 3x squared. And 1/4 times 3 is 3/4, because you can think about this, 3 is 3 over 1. So this is 3/4 x squared, which is what kind of shows up over here as part of the derivative. This 1/4 x cubed produces this 3/4 x squared. And much like the power rule, I won't prove this fact to you, but I do want to make one little comment just because I can't help myself. In a pre-calculus class, you may have learned about function transformations. If I have some function f of x here, and I'm interested in the graph of, 3 times f of x, this 3 acts as a vertical transformation. Essentially what it does is it takes this graph and it stretches it vertically by a factor of 3. So instead of the graph looking like it looks in green, it follows kind of the same pattern, except it's a lot taller, so it sort of looks more like this. Maybe that's poorly drawn, but it gives you the idea. The graph in pink and the graph in green have kind of the same shape. The graph in pink is just more extreme, if you want. Now let's think about the slope of the tangent line to a point for the graph in pink. So pick any arbitrary x value you want. It doesn't matter which one. Consider the slope of the graph in green and the graph in pink at this specific point. They're very related, right? They're both positive. It's just pink is going to be steeper. In fact, it's going to be 3 times steeper because we've stretched this thing vertically by a factor of 3. And that's not true just for this point. That's true for any point. Because all this 3 does is it stretches the graph vertically by a factor of 3, what that's going to do to the slope of the tangent line to any point of the graph is it's just going to make it 3 times as steep, which is exactly what this statement here is saying. The derivative of a function that is stretched vertically by a factor of a is just going to be a times the derivative of that function. It kind of makes sense that these coefficients don't interact with the derivative because they're just making the graph that many times steeper, which we account for by putting a coefficient in the derivative because the derivative represents the steepness of the graph, loosely speaking. Does that make any sense? You follow that? I mean, the good news is you don't have to because it's a business calculus class. If you can take the derivative of 10x to the 20th power. Oops, looks like I wrote the wrong thing here. I don't want to go back and re-record the whole video, so maybe I'll just scratch this out and make this 200x to the 19th. At least I did it right down here. Anyways, I got one more rule to show you before I'm done with this video. I know it's a little bit long, but I think it makes the most sense to put all 3 of these in the same video. So the last rule that I want to show you, and I kind of want to change some of the words in here. I don't want you to guess at what this is equal to. I just want to look at this example and see if we can come to some conclusions that you may have already come to. The derivative of 4x to the 5th minus 6x squared, it turns out that's 20x to the 4th minus 12x. Maybe you'd stare at that for a minute and be like, wait, is it? Oh yeah, obvious. I already knew that the derivative of 4x to the 5th, first using my coefficient rule, is 4 times the derivative of x to the 5th. And then using my power rule, it's 4 times 5x to the 4th. And then because 4 times 5x to the 4th is 20x to the 4th, I already knew that the derivative of 4x to the 5th was 20x to the 4th. And similarly, I knew that the derivative of negative 6x squared, first using my coefficient rule, would just be negative 6 times the derivative of x squared. And since I know the derivative of x squared is 2x, it's negative 6 times 2x, in other words, negative 12x. I already knew that the derivative of 4x to the 5th minus 6x squared is 20x to the 4th minus 12x. And here I'd be like, actually, I don't know that you did. You knew the derivative of this part was 20x to the 4th, and you knew that the derivative of this part was negative 12x, but you did not know that when you were taking derivatives of sums and differences, you can just take the derivative of each part individually and then add them back up. Turns out you can, which is awesome, especially for polynomials. It turns out that anytime you're taking the derivative of a sum of 2 functions, all you gotta do is take the derivative of the first one and then add the derivative of the second one. And it turns out that works with not just sums, but also differences, because we can treat the negative as part of the coefficient out in front and use the second rule that we learned in this section. So this result will end up being really nice for our purposes. What I'm hoping you got out of this video is 3 different results. The first one is this power rule. When you're asked a question like the derivative of x to the 6th power, it would be nice if you could immediately tell me that that derivative was 6x to the 5th power. The second rule I want you to understand is the coefficient rule. That if you're not just asked for the derivative of x to the 20th, but instead 10x to the 20th, you don't have to do anything with the 10. You just multiply the answer to the derivative of x to the 20th by that 10 at the very end. So if you can see that the derivative of 10x to the 20th is 200x to the 19th, that's fantastic. And then finally, when you have sums and differences, like the derivative of 4x to the 5th minus 6x squared, If you understand that we can just take the derivative of each of the terms individually, the derivative of 4x to the fifth using our power rule and our coefficient rule gives us the 20x to the fourth, and the derivative of negative 6x squared gives us the negative 12x, then you've picked up everything you need for this video.